Okay, so let's get started here. Okay, hello everyone and welcome to our Econ seminar today. My name is Ivan Ortega and it is my great pleasure to introduce Tran Nguyen today. Tran, I apologize if I mispronounce your last name, and thank you very much for accepting the invitation. Tran is joining remotely from California, but I hope next time we can invite you over for an in-person seminar. Okay, so a few words about Tran. Tran graduated from the University of Southern California in 2007 with a major in chemistry. Then she transitioned to her PhD in chemistry at the University of California, Irvine. And Tran obtained her PhD in 2012. From 2012 to 2015, Tran was a Steinbach and NSF postdoc fellow at Caltech. Currently, Tran is an assistant professor at environmental chemistry at UC Davis. And Tran is also the director of ICAROS, an NSF database for atmospheric chamber research. And she is also a recent recipient of the Career Award. Tran's research interest includes fundamental oxidation chemistry in the atmosphere, both in gas and condensed phase. She is also interested in aerosol chemistry that impact inhalation exposure and toxicology. For example, e-cigarette aerosols, biomass burning aerosols, among others. And now, today we are using Slido to post questions, which you can ask at any time during the seminar. Most of you might be familiar with Slido, but if you are not, you can scroll down the web page of the presentation and you can see the Slido interface at the bottom of the web page. Questions will be passed to Tran at the end of the presentation. Again, thank you so much, Tran, and welcome, and please take it away.
Thank you, Ivan, for that kind introduction. It's my pleasure to be here. Thanks for inviting me, giving me the opportunity to share my research with you all. So today I'm going to be talking about the kinetics, organic acid yields, and atmospheric impact from aqueous photochemistry of isoprene-derived organic aerosol compounds. And I'd like to thank the National Science Foundation for funding this work. So just to go off, just to start with our motivation for this work, I might not need to introduce isoprene to this crowd. We're aware of its importance for atmospheric chemistry, given its enormous emission flux. And over the past almost 20 years, our community has made enormous strides in understanding the gas phase photochemical cascade of isoprene. Mainly its reaction with the OH radical, but also ozone and nitrate, producing oxidized VOCs. And there's been important discoveries like the formation of intermediates that ring open to form condensed phase compounds, or will partition through equilibrium partitioning. But then what happens when the organic aerosol compounds are formed and they're dissolved in the atmospheric aqueous phase? Well, after that, our knowledge really falls off fairly sharply. From the most recent review of isoprene's chemistry by the Caltech group, Paul Wenberg, for example, stated that even though there are group additivity approaches to understand the condensed phase reactions, it's clearly inadequate for simulating condensed phase reactions of isoprene compounds. And the challenge remains enormous given the incomplete knowledge of the rate coefficients of condensed phase chemistry. And likely because of this, biogenic areas in which isoprene tend to dominate are often poorly represented in models. And this includes tropical or boreal forests in the Southeast United States. So this signals to us the importance of fully understanding all of isoprene's chemistry, including its condensed phase compounds. For one, surface ozone is overestimated, and that is most severe over the Southeast United States when you have big biogenic emissions combined with high NOx emissions. Organic aerosol burden is recently overestimated when we try to include all that we know. I should say almost all, but almost all that we know about the formation pathways of isoprene SOA. Now we're overestimating the organic aerosol burden. And this has been appreciated in our community for a while, but formic and acetic acid is underestimated. And this could be for a variety of reasons. There's been a number of observations and hypotheses. But what we know is that the underestimation of formic and acetic acid can be seen by satellites, surface observations, and surface exchange fluxes. We know that it's majority biogenic, a good amount of it is secondary, and it can't really be understood just from the gas phase chemistry of isoprene. So it is my hope to convince you by the end of this presentation that our hypothesis that incorporating the photooxidation of isoprene aerosol compounds in models, that we can help reconcile all these biases in the right direction at the same time. So alluding to the challenges that remain for understanding this chemistry, I'm going to go into 3 reasons why perhaps this isn't as far along as we'd like, and talk about how we overcame them to study and come up with some of these kinetic coefficients and mechanisms and model impacts. For one, isoprene SOA compounds, they're fairly complex. They have multiple functional groups on them. They can't be found on the shell. Some of them are quite unstable. So in order to study any of them in any meaningful way, we really have to synthesize them. So organic synthesis has opened doors for a number of recent studies, and we're going to exploit that for further understanding. Second is, in order for us to get yields of formic and acetic acid from aerosol aging in a chamber, for example, that is extremely difficult because of the competition from chamber walls. So especially if you do this in a humidity dependent way, you end up trying to target a very variable yield of formic and acetic acids from chamber walls. So it's a moving target, and it's also subtracting a very large number. So this is hard to do. And this was described well by a recent paper by Michael Link. Also, in order to represent this chemistry in models in a way that's chemically specific, we would have to have a model framework for understanding the chemistry, the multiphase chemistry from specific molecules. And that's not present for a number of common global models. Sometimes you would see SOA represented as one species, so SOA. And then how would you describe all the specific chemistry from all the SOA compounds? So those are the challenges that I'd like to focus on. I'm sure there are others. But in order for us to address, one big challenge is we don't know the kinetics. Our first study is to understand how fast OH reacts with some common isoprene-derived organic aerosol species in the bulk aqueous phase. And this work was led by my undergraduate at the time, Teresa Avalar, and it's been submitted to Environmental Science and Technology. So basically we have 7 compounds that are either from the isoprene photooxidation system or related. And then we determine its bimolecular rate coefficients. Okay, so let's go back into to the photochemical pathways forming these species. So I've circled the ones that we're studying. From isoprene, you're gonna add OH radical to either here or here, right? To these are the major peroxy radicals that you're going to form, either the tertiary or the secondary. And then when in a low NOx condition, you have HO2 forming the hydroxide peroxide, which then in a OH neutral pathway forms IEPOX, the epoxidiols, which then ring open to the methyl tetrols with water, or the methyl tetrol sulfate with sulfate anions, and that can hydrolyze back to methyl tetrols. Sulfate is thought to be in the tertiary position here, but with this peroxy radical, if you have high NO, you form the alkoxy, and then a minor channel goes to isoprene hydroxynitrates, right? So with this tertiary nitrate, what it can do very quickly is hydrolyze to the alkene diol. In this case, we have the 1,2-dihydroxy U3-ene, so I call it MDE. Now, these isoprene nitrates can react further and form the isoprene dinitrates. With this dinitrate, with two nitrate groups, one in the tertiary and one in the secondary position, the tertiary one can hydrolyze very quickly to form the trihydroxy mononitrate, right? And then in a high NO2 pathway, well, first with NO, you make methacrylin, and then methacrylin can react by OH abstraction at this the aldehydic hydrogen, and you form the acyl radical, and then you form the MPAN methacrylyl peroxynitrate, and then the MPAN can oxidize to form a alpha lactone, HMML, which then ring opens to 2-methylglyceric acid. So these are the compounds that we're focusing on, right? That we think are major contributors to the isoprene SOA. Oh, I should also mention that we have an analog of the sulfate with only 2 OHs, in which we made by accident, but we studied it anyway. So in order to get to these compounds, you have to synthesize them. Luckily for us, the literature describes the reaction to a number of compounds already from the IEPOX pathway. So starting from 2-methyl-2-vinyl-oxirane, we can actually make the MDE simply by ring opening it with acid. And then so with the MDE, we can epoxidize the alkene group with MCPBA to make the delta IEPOX here, which then we ring open with acid to the methyl tetrol, or with tert-butyl ammonium sulfate to the methyl, the 2-methyl trihydroxy sulfate. In this case, we have the sulfate in the primary position. And over here, we actually can ring open, can sulfate the alkene group of MDE to a dihydroxy sulfate, and the sulfate in the secondary position. But in order for us to study everything that we wanted to, we actually have to come up with novel routes. So we synthesize the mono nitrate and the dinitrate from isoprene. So isoprene, we can brominate it, and it's going to go almost exclusively to the 1,4 dibromo compound. And with this dibromo alkene, we can nitrate it with silver nitrate to the dinitroalkene. And then we can oxidize this double bond with permanganate to the 2,3-dihydroxy 1,4 dinitrate. But also from 1 here, we can acetylate the bromine and then hydrolyze to the diol, and then brominate the alkene to the dihydroxy dibromo, and then nitrate it. And we actually do make this compound, but it's just gone so fast that we can't study it. So we end up with the nitrate group in the secondary position, and then this tertiary nitrate hydrolyzing to an OH. So with that, we can undergo study, and we buy the 2-methylglyceric acid because we are able to get it through a custom synthesis request through a company, and that's way better than doing it ourselves. So that's what we did. So if you note that there are 2 isomers that are studied that are not the major ones, even though the major one of the dinitrate is synthesized, it's not going to be available for study. So just note that. So with that, we can then study the kinetics using a competitive rate study, and we choose a reference compound erythritol, in which we know the OH rates fairly well. And so here is 2-methyl-tetrol and erythritol together. You can study how both of them are reacting with OH radicals. With this, we choose to monitor the reaction with high-performance liquid chromatography coupled to high-resolution mass spectrometry. And I'm going to be referring to this technique as HPLC-HRMS throughout this presentation. And then there are some that we choose to do nuclear magnetic resonance, NMR. This is just proton NMR. And the reason we chose this for the alkene diol MDE is because the alkene protons are so unique that it's a very clean way to monitor this reaction. And since we have all of our compounds and erythritol, we can study the ratio between their rates. Right? So we come up with all these ratios. Some of them are faster than erythritol, in this case, the alkene, no surprise, and most of them are slower. The 2-methylglyceric acid, since it's an acid, we actually study it at 2 pHs. But unfortunately for this compound, it is the most uncertain. So it's possible we don't really know how the rates change within those pHs. Unfortunate, because there are some that the uncertainties are very small based on the analytical methods that we're using. So with this, we can formulate a table. I'm not going to go through the table in detail, but compared to erythritol at 1.9 times 10 to the 9, adding a methyl group, or if I can reframe that as taking away an abstractable hydrogen, a secondary hydrogen, and replacing it with primary hydrogens, it reduced the KOH by almost a factor of 2. And then if you change out one of these OHs with a sulfate group, you increase the rate. That's interesting. And then you're going from a trihydroxy to a dihydroxy, but the sulfate's in a different position. The rate decreases by a factor of 3. The MDE is fast, not as fast as something like methacrylate, but then you have something like the dinitrate, and it's slower, right? The mononitrate is sufficiently fast. And then when you have 2-methylglyceric acid, that's very comparable with the 2-methyl-tetrol, but I would say indistinguishable in this 2 pHs. Okay, so what does that mean for our understanding of chemistry in the atmosphere, and whether or not common models like GEOS-Chem is representing this chemistry? So for things like 2-methyl-tetrols, GEOS-Chem will represent IEPOX, its precursor, and then it'll make 2-methyl-tetrols, and then everything is treated as photochemically inert. So 2-methyl-tetrol is not lost unless the particle deposits. And that has a lifetime on the order of days, maybe several days. So what if we assume a certain OH concentration in cloud water or particle water? And I'm just taking these from the Herman et al. 2010 review as mean concentrations. In that case, we're going to see that the cloud lifetime is going to be about a day, and for particle water is about an hour. So oxidation is going to win. In this case, it's not going to wait for the particle to deposit. When you have the 2-methyl-tetrol sulfate, well, this can now undergo hydrolysis. Even a tertiary sulfate, the hydrolysis lifetime is pretty long, like 60 to 460 hours. And this is pH dependent. But it'll also be lost through particle deposition. Now, with the rates that we determined, we can give a range of 18 to 55 hours in clouds, 1 to 3 hours in particle water. And the range is because we studied the primary sulfate, and based on the literature on how different functional groups in different positions will change the rate, we think that there's a factor of 3 range. So this is the conclusion here. But that doesn't really matter because it'll still win. Oxidation will still win. As for the main isomer, the 2,3 dinitrate, well, hydrolysis is super fast, and so fast we can't even study it. So oxidation does not win. This compound is definitely going to get hydrolyzed. For the minor isomer, with the nitrate in the 1 and 4 position, well, now hydrolysis is very slow, and the particle deposition is going to be on the order of days. So this is a slower OH rate, and then we're getting something like 112 hours in cloud, 6 hours in particle. So particle wins. Cloud is like a tie. But for this compound, the 2,3 dinitrate, when it gets hydrolyzed, the hydrolysis lifetime of a secondary nitrate is actually pretty slow still. And so compared to this oxidation, the oxidation is going to win. Now with that, we can start thinking about, so now we know that these compounds oxidize fairly rapidly. We can talk about the yields of formic and acetic acid from the OH oxidation. And this is coming from my postdoc, his paper recently in ACS Earth and Space Chemistry, the Mario Molina special issue. This is studied in the aqueous bulk, and excuse me, we only studied 2-methyl-tetrol and erythritol in this paper. So I'm going to go through our experiment design, 2-methyl-tetrol versus erythritol, so without the methyl group. And what we do is just add hydrogen peroxide to initiate photochemistry and light. And then we monitor how much of that goes to formic and acetic acid. So this is an NMR study. So this is done in an NMR tube. So there are 2 ways that the reaction is monitored. First, the reaction mixture is on the outside of the tube, and we have an internal standard in a sealed capillary dropped inside. And here, the reaction mixture is in the sealed capillary, so there's no headspace. And then the internal standard is on the outside. So we compare the two to see what are the yields and reaction rates like when there's no headspace versus when there is. So we introduce UV light, and then we monitor the reactions at several time points. We use proton NMR, carbon-13 NMR, and we also derivatize the reaction mixture with dinitrophenylhydrazine, and we look at it with HPLC RMS to see what carbon yields are being formed. So this is what the reaction looks like for erythritol. At time 0, you just have the internal standard in erythritol. And then as the reaction goes on and on, you form things like glycolic acid, formic acid. We think this is a sigma acid, but it's just really small. This might be acetic acid. I'm not sure where that would come from, but there's not that much in terms of major products that are being formed. There are some minor products that you can see squiggles here. I don't have time to go into what all the minor products are, but we do have that in the paper if you're interested. So with the 2-methyl-tetrol at time 0, you have there's this methyl group here, and then the rest of the methyl-tetrol, all the polyol hydrogens, and those will go down, and then you're forming formic acid, glycolic acid. Now you have substantial acetic acid, not a whole lot else that is being formed, interestingly. So if you monitor the reaction over the reaction time, in this case is 24 hours, we can see the 2-methyl-tetrol go down, the formic acid go up, acetic acid go up. These uncertainty bounds are due to repeated experiments. And then you can see the difference between erythritol and 2-methyl-tetrol. With erythritol, we have glycolic acid being a first-generation product. It formed very fast. But then formic acid is formed slowly over the course of a day, but it rises fairly slowly. For the 2-methyl-tetrol, now you can form acetic acid, but you still have the same shared first-gen product in glycolic acid, but then you have acetic acid and formic acid being formed at roughly the same time scale. So this is now a first-generation product. So that's the first difference. right? They're formed promptly. And another interesting thing is that with erythritol, we see this first generation trihydroxycarbonyl. So imagine erythritol has two sites for abstractable hydrogen. So you abstract here with OH, and then you lose HO2, and you get this trihydroxycarbonyl. And we actually see two isomers. Probably the major one is the ketone, and then the minor one is the aldehyde from abstraction of its primary. For 2-methyltetrol, could form a very similar compound, but we really don't see that formation much. And we think, based on all of the NMR and HPLC data, that stable intermediates are not as significantly formed from the 2-methyltetrol. Based on the spectral evidence, we're able to propose a mechanism. So from erythritol, this is the minor pathway going this way, okay? OH abstraction, peroxy radical forms, alkoxy radical, when it bumps into itself or solvent compounds, scission to major compound, the major product is glycolic acid, forms another peroxy radical. With this one, delcoxy, and then you get glycolic acid. So 2 glycolic acids and no formic acids as the major species. There's a minor channel that can get you formic acid, but it really doesn't want to cleave this way, given that this is the thermodynamically favored alkyl radical. But for the 2-methyltetrol, when you go through the exact same process and you end up here at this alkoxy radical, now this alkoxy radical in the erythritol has a methyl group here. And so the major fate is going to be scission to the acetic acid and then formic acid. So what you get in one generation is glycolic acid, acetic acid, and formic acid in the same go, and some minor formation of the larger compounds. So that's what we think happens. And then when you have formic acid and acetic acid, glycolic acid, well, at long time scales, you're going to form CO2, right, from the decarboxylations. So if we start at 0 hours, this is carbon NMR now, we can see that all the carbons of the 2-methyltetrols are here. And then this is just the solvent, CdCl3, and the internal standard here. There's nothing going on at time 0, but at 18 hours, now we can see that we have acetic acid, we have formic acid, we have CO2, and those are the only things that we see. So that means that eventually that's all that's going to be made. So I'm going to talk a little bit about the suppression of the volatile partitioning. We know that doing experiments this way, we're going to be limited in the formic acid and acetic acid that we're observing in the aqueous phase. So we tried to shut down that partitioning. So for erythritol experiment, you can see that the formic acid formation in black here is the experiment with the headspace, and in blue here is the experiment without the headspace. And there's a 60 to 80% increase of these acids for glycolic acid or formic acid. We do the same thing for 2-methyltetrol. We get an increase, but not by that much, 14 to 17%. And we think that it's because we did the experiment not as well, to be quite frank. It's really hard to flame seal something and get 100% of the air out. So with those, we decided to have bounds instead, so 15 to 85%. So with that, how much carbon can we account for from the 2-methyltetrol? Well, from formic, acetic, and carbon dioxide that we account for at 18 hours, it's about 50% of the carbon. And if we did that partitioning estimate, at the lower limit, we can account for about 60% of the carbon, and upper limit, we can count to like almost 100% of the carbon. So now that we know that most of the carbon is in just 3 of these compounds, let's see if we can represent that in a model. In a model, we want to be able to model at all pHs that at least, you know, the binary condition of the acetic acid and formic acid being in its neutral or deprotonated form. So we did experiments at pH 2 and pH 9. And with the OH exposure going upwards at pH 2, the formic acid forms and levels out, acetic acid forms, levels out. But at pH 9, when you form the formic acid, it becomes formate right away. And the initial formation is high, and then formate reacts away very quickly because of this higher rate coefficient with OH. Acetate will form and also react away. Now, acetate and formate, once they're formed, don't really leave the aqueous phase. So there's a couple things going on, but we think that partitioning is just a part of the story, not the entire story. If you choose any particular OH exposure or time, and you just ramp up the pH, you can see that the pH, the yield of the carbon here goes from 2% to like 16% almost, you know, for formic acid. And there's some sort of yeah, so honestly, this transition pH point doesn't match the pKa, and we think it could just be to a variety of conditions. One of the reasons being that this is not just pure water, but also is not just some sort of equilibrium, but also it changes the formation yield as well. And so we decided to model, have a condensed model for a condensed mechanism that can be inserted into a global model. And it's really not meant to map to a real reaction, but we have to balance out all of these processes to understand what's the bulk formation of formic and acetic acid. So at pH 9, it's actually fairly simple. The 2-methyl-tetrol plus OH, we have K1 that's constrained by experiments. All we have to do is have a formate and acetate yield and glycolate yield, and have glycolate go to formate and CO2, and have the known chemistry of all of these things, and we're able to actually represent all of the reactions very well at pH 9. At pH 2, there's a lot more going on apparently, so we need another generation of chemistry and unknown products in order to represent that. But all that aside, we can estimate that the gross production yield of formic acid from all these pathways, and then accounting for the partitioning, is about 2 to 3 formic acids per methyl tetrol, and about 1 to 2 acetic acids per methyl tetrol. So that's a lot. This is not in James's original paper, but then we started doing the organosulfate as well. And we can represent its chemistry fairly reasonably close to the 2-methyl-tetrol. And we get something like 2 formic acids and 1 acetic acid. So these are big yields. Let's see how much time I have left. So with that, I apologize if I'm going a little bit quickly, but I can answer questions afterwards. With that, I would like to move on to our experiments on the heterogeneous system, like what this reaction is like now on the surface of suspended particles. And this work is in preparation, so it's not published yet, it's just preliminary. And we do this in our 10 cubic meter Teflon chamber. So here is my chamber. It actually sits into a big refrigerated room. And it's refrigerated as in insulated, but so it can go to -20, but it can also go upwards to 60 degrees Celsius. And we can inject particles as well as gases. And then we have a triple quad CF3O minus SIMS. So this is the Caltech style SIMS. We have a SMPS. The AMS is not on here the whole time, but we can borrow it. Ozone, NOx, relative humidity, temperature, and a GCFID that we can use to monitor hydrocarbons. So with the experiment, what we do is adjust the relative humidity and temperature that we want. And then we start our instruments. We inject ammonium sulfate mixed with the organic that we're interested in. In this case, is sorbitol to represent 2-methyl tetrol, because 2-methyl tetrol is still kind of volatile. And then I want everything in the particle phase, or the 2-methyl tetrol sulfate, which is definitely going to be in volatile. And so we mix it with ammonium sulfate and we inject it in deliquesced. And as it enters the chamber at different relative humidities, it loses water, but it doesn't effloresce. So it maintains different amounts of particle water on it, depending on the size. Now inject our OH precursor, which is methyl nitrite. And we do this because we want all the OH in the gas phase. And the the methyl nitrite has a very low Henry-Saw coefficient. And we turn on the light and we produce OH in the gas phase, and we see our particle get reacted away, and then we see formic acid and acetic acid being formed. And that's basically the experiment. So it sounds simple, but there's actually a lot that goes into a data point. The first is we need to understand how much OH we're producing. And with that, we do a kinetic competition with cyclohexane. And the cyclohexane, we use a GCFID to understand the decay, SMPS to understand the decay of the particles, and we introduce something like 2 × 10^8 molecules per cubic centimeter of OH in there. Then we clean it. And then in order to get one data point, we actually have bounds. So what do the walls look like when they're relatively clean? And so how much formic acid does the wall plus OH produce at that relative humidity? And then we do an experiment. So we inject the particles that have our sorbitol or 2-methyl tetrol sulfate with OH. That happens at the same time as the walls being oxidized with OH. And then our after control, then we flush it, but we don't clean it. And then we introduce methyl nitrite again, the same relative humidity, and see what the dirty walls look like. So with that, monitor the particles with SMPS. And then with the acids, we actually collect everything through a DNPH cartridge. And we use HPLC, HRMS to study that. So I'll show you what it looks like. So this is a little cartridge. My undergrad student, Lillian, drew this. Has all the proper shading and everything. It's very impressive. So you suck the air out, and then it gets derivatized in situ to a hydrazone in the DNPH cartridge. And what we do to test the derivatization efficiency and collection efficiency is when we put the formic acid in a bag, we measure the flow, and then we derivatize it, and then we see what the signal is. And we actually synthesize the authentic standard and then see what concentration we get. And if that matches the concentration that we put in the bag, we calculate the derivatization efficiency. And it was actually really close to 100%. So the collection efficiency is we have different cartridges in series, and we can see that we get 100% of the signal in the first cartridge and almost 0% in the second and third cartridge. So we know that the first cartridge captured almost everything. So this is what the hydrazone looks like, and this is the exact mass. So with the particles, when we introduce the sorbitol or 2-methyl tetrol sulfate mixed with the ammonium sulfate, this is the number distribution. And with every relative humidity, we actually have to do a correction for particle wall loss that's dependent on both the humidity and the size of the particle. So we introduce the exact particle type that we're interested in. So we don't use just ammonium sulfate or anything. We use this mixed sulfate, ammonium sulfate with organics, and map out the wall loss rate at every diameter at all the RHs. And with that, we can use it to correct the experiment. So here in the blue is the SMPS measurement of particle mass. We inject it, let it kind of equilibrate a little bit for an hour. You can see it kind of goes down. And then with the lights being turned on and methyl nitride being introduced, it decreases. And then at this point, there's almost no more methyl nitrate. So this is basically wall losses at this point. So once you correct it, the way that you know that you did it right is at the beginning, when there's no chemistry, the trend should be basically 0, right? And then the photochemistry decreases it. And then when the photochemistry is exhausted, there's nothing else. And this amount is how much we had consumed to produce the formic acid. And the formic acid yield is FA moles over, this is in mass, but you can convert it to sorbitol or methyl tetrol sulfate reacted by mole. And what we get is this. When we do the reaction on sorbitol at 20-something%, 25% relative humidity, we get something like a 40% yield. And then at 80%, we get like 60% yield. And these are the bounds of the walls. For methyl tetrol sulfate, we actually get 90-something% at 80% humidity. And acetic acid is very low at this point. Now, I have to say this is preliminary because we are not done with all the quality control measures for acetic acid yet. So this could change, but it looks lower. And the reasons why it's lower, I am not sure I can tell you. So if you look at the results for heterogeneous oxidation versus bulk oxidation, at this point, at this OH exposure in the bulk oxidation up to methyl tetrol sulfate, it's around 2 to 4 atmospheric days in a cloud, I want to say. And then over here, it's about 8 atmospheric days of OH exposure in the gas phase. So I think there's some interesting differences, but since this is preliminary, I don't want to get into speculating everything. I do want to say that it seems like with the particles that the yield per carbon of formic acid is very, very high. And it could be due to surfaces or something. So now, with my remaining time, I want to talk about Kelvin's work, Kelvin Bates, who is a visiting scholar between my group and Danielle Jacobs group at Harvard. He is inputting these yields and kinetics into the GEOS-Chemical model to help us understand what is the impacts of these aerosol, isoprene aerosol photochemical sinks on atmospheric formic acid, acetic acid, but also on the organic aerosol budget. Okay, so organic aerosol, as I said at the very beginning, had been overestimated. So in recent years, the community started putting in like mechanistic SOA pathways and IEPOX into GEOS-Chem. And they found, so this study from Pai et al. Found that over a bunch of different field campaigns, that the complex model overestimates many of these field campaigns, the ones that are especially in biogenic-rich areas, and an aggregate of everything is overestimate with complex model and nearly no bias with the simple model. But the simple model is getting things right, not for the right reasons. If you look at the overestimate of the organic aerosol burden, one of the things to note is that even though we're inputting in a bunch of mechanistic SOA pathways to form SOA, there are not accompanying sink pathways to remove OA. So there could be, that is the reason for the bias. And what Kelvin's doing is adding in these photochemical sinks based on our new data. So here in GEOS-Chem, you have this species OA, which he was able to differentiate in the model. you have sources, both primary and secondary sources to form them. And then you have the removal, which is dry and wet deposition. So what he's adding is photochemical sinks, OH radical. And he started with the scheme, the aqueous photochemistry scheme by Dylan Millett's group at University of Minnesota. But we had to modify that even more. And as a preliminary measure, we're only going to consider two compounds, the 2-methyl-tetrol and the 2-methyl-tetrol sulfate. This is what the modeling scheme looks like. So that you have primary OA from anthropogenics, but actually I think marine, yeah, this is marine, counts for, a major source burden. And then you have your secondary OA from isoprene, terpenes, fires, and anthropogenics. And then with isoprene SOA, so that this is how much it contributes. You speciate that out to methyl tetrols, 2 teragrams per year for organosulfates. Then this is global. So in a regional area like Southeast US, it might be more relatively. But then there is 22 teragrams per year of other. The organic nitrate, some of them, a big portion is from isoprene, and then 1 from monoterpenes. Then you get all of these terpene SOA species, and then all these aromatic SOA species, which I think Kelvin started putting into the new revision of GEOS-Chem. Okay, so what we did is just take these two up here and implemented the loss pathway. So what we found is that the updated scheme really improves the OA burden, but the story is even more complex than that. I'll explain. So the simple model has an OA burden of 1.94 teragrams. And here's the primary versus secondary split in sources. It's about even. And then wet and dry deposition removes 23 and 123 teragrams per year. So here's the key. So P with a quotation mark around it is because sometimes oxidized POA is also considered POA. So it's not, totally POA. But SOA, you have anthro and biogenic, and then the terpene, and then isoprene and organonitrate. And these are the key color codes. So in the complex scheme, now the oxidized OA got increased. And actually that took away a little bit from the secondary. But what was communicated to me was that this complex scheme overestimated the OA burden by kind of a lot. And there were more OA pathways, formation pathways that the GEOS-Chem community wanted to put into the complex model, but had to stop because it was already overestimating the SOA so much. And then so this is now almost similar amounts being removed. But in our updated scheme, which is going to be included in a future update with GEOS-Chem, is we have photochemistry now for the 2 species, and that removed a lot, right, just for the 2 species. And that got us really close to no bias in the OA burden, and I think starting to be for the right reasons. Now, you might notice that the secondary SOA source is much higher here than the complex scheme. Is now everything that they wanted to put in as additional sources, everything we knew, they could finally put into the secondary OA source because it's balanced out by this huge photochemistry sink. So with this updated model, we're getting close to the OA burden, and we're getting close to being able to put in all the chemistry that we know occurs. So this is good news. So what happens in the global map, changing from the simple scheme to the updated scheme? Well, not surprisingly, so the new sources are going to be, around the isoprene area. And the net change in SOA from the photochemistry is even though there are new sources, there is negative net change in the areas where the OA burden was overestimated most egregiously before. And then from a formic acid standpoint, previously the source of formic acid was 60 teragrams per year. Now we know that the source is likely much higher than that, maybe a factor of 2 higher. But the new sources from 2-methyl-tetrol and 2-methyl-tetrol sulfate added at 8 teragram per year source strength. And if you compare that to all the aromatic chemistry that had been added, it's more. So this is not a silver bullet from these two compounds, but it actually added a lot globally. But regionally, you can see where the impact is because this 2-methyl-tetrol and 2-methyl-tetrol sulfate is going to be highest in regions like the Southeast US, Congo, maybe some areas of Amazon. And it actually increased the Southeast US formic acid by about 300 ppt when there was an underestimate of 1,500 ppt. So approximately 20% of missing formic acid can be reconciled by the chemistry of 2 isoprene-derived compounds. So our conclusions right now is that most of the isoprene-derived organic aerosol compounds will be removed by oxidation. Some of it quite competitively with other fates, and some of it would be an overwhelmingly dominated fate. So organosulfates, this appear to be true. All the hydrolysis of inert organonitrates, including the trihydroxy mononitrate in the secondary position, all of this is going to build in concentration because it's not being removed by hydrolysis. And then since it's building in concentration, it's going to get removed by oxidation. And these photochemical losses are going to be needed in models to balance out all the sources that have been discovered recently. And just the 2 isoprene SOA compounds make a big difference. We saw that the 2-methyl-tetrol, erythritol, and 2-methyl-tetrol sulfates do make formic acid in hugely nearly quantitative yields. Also, acetic acid if they have a methyl group, and effectively in 1 generation from 2-methyl-tetrol. And these reactions are likely ubiquitous to different amounts of different kinds of polyols and their analogs in the atmosphere. And we think preliminarily the particle surfaces changes the yields. So I have additional thoughts is that if we can input in the loss rates for these 2 compounds, what happens if we did it for everything else? I mean, we have the rates here for the isoprene hydroxynitrates. And how about things like the fire EOC and the fire SOA? Well, there's a lot of levoglucosan, and this is a polyol as well. And we already know that biomass burning, there's a big fraction of missing formic acid from there, and that the formic acid emission from tropical fire plumes is substantially secondary. We know that because the formic acid versus CO ratio is too high. So this could help reconcile that as well. And then what about terpene, SOA species, and all the rest? So I would just leave that as additional concluding thoughts. So thank you for your attention, and I'm happy to take any questions so far.
Thank you, Tran. That was very nice. Again, everyone, if you have questions, please submit your questions in the Slido interface. I think we have a delay of about 20 seconds or something like that. So we might be getting some comments or questions in a little bit. So in the meantime, I have some questions, a couple of questions. I'm not really into like experiments, chamber experiments, but I always try to understand like how do you translate that into the atmospheric conditions? For example, your second part of the chamber experiment, or the chamber experiment. So the formation of formic acid, you mentioned like you might have like OH of about 210 to the 8 molecules per cubic centimeter. And at the end, you explain a little bit like the atmospheric conditions and how do you translate that? So can you, but it was really quick. I didn't quite understood, like, how did you
Yeah.
translate that into the atmospheric condition?
Yeah, that's a fantastic question. And I neglected to say that since these are preliminary data, we're also adding in experiments. And a part of the experiments that we're adding in is we're going to vary the OH oxidation exposure. So exposure at 1 times 10 to the 6, 1 times 10 to the 7, 1 times 10 to the 9, and just to see what all of that does. Because since we have a reaction time of about 1 hour, we can then change the OH steady state and get different OH exposures that way. In that case, that's going to make it a lot easier to extrapolate to different atmospheric conditions. Yeah, thanks for that question.
Yeah, I don't see questions. So my second question was about, I didn't quite understand the headspace you mentioned in the first part of the talk. What is the headspace and how does that affect the results?
Yeah, definitely. So do you, let me see if I can go back. So in this case, we have a little tube, if you can imagine, like that. And we're doing a reaction in water, right? And if we're photolyzing the reaction mixture and we're producing something volatile like formic acid, a lot of that's going to be removed, right, from the aqueous bulk. There's going to be some diffusion limits on how fast it can be removed, but there is some sort of headspace there, right, where things can partition from water to air. So in that case, maybe the formic acid that we're seeing in the tube isn't the full formic acid yield. You know what I mean?
Yeah. Mm-hmm. Yeah.
So if we did a reaction when we can magically remove all of the air that it can partition to, then we wanted to see how the yields would enhance if we did remove that headspace. And that's why here we devised an experiment where the internal standard was on the outside and the reaction mixture that's being photolyzed is on the inside of a sealed capillary, which we tried to get all the headspace out, and to see what's the enhancement in formic acid yields.
Okay.
Yeah.
Okay. Okay.
I hope that's clear. Yeah.
Yeah. Yeah. I can read the article too. I don't see questions. Please, if you have questions, submit them now. I don't see questions. Interesting. Everything was very clear. Let's see. I don't see questions. Let's give them a few seconds. There is a question from Eric Apel. I can read it for you. So Franco et al. Recently published atmospheric chamber experiments that show that formaldehyde is efficiently converted to formic acid via multiphase pathway that involves its hydrated form, methane diol, which went far to explain measurement model discrepancies for formic acid. How do your formic acid results fall into those in reconciling model and measurements comparisons?
Yeah, so I'm aware of that study, but I don't think I'm the best person to comment on that. I might leave that to modelers. As far as I know, that's a cloud source, and it's big potentially. But what uncertainties can be understood from the constraining experiment in that work, I think we're going to have to let the global modeling community figure out how best to incorporate all the sources of formic acid into their models and see which ones have constraints and see which ones affect the formic acid discrepancies in the right area. So for me, I'm a experimentalist, and I could tell you what my results are, but I can't tell you whether or not my results are better or more relevant than anyone else's results. But that's why we have amazing modelers that can take in all the data from our community and really give a comprehensive overview of what they mean.
Okay, thank you. So there is another question from Jeff Tyndall. Great talk, Tran. In Kelvin's work, you say there was a big photochemical sink of SOA. Is this with OH or photolysis?
Thanks, Jeff. This is with the OH oxidation for the 2-methyl tetrol and 2-methyl tetrol. Is directly from our aqueous bulk work. Does that answer your question, or is there a follow-up?
Probably he can comment, or I'm sure he can contact you if that was not clear.
Okay, thanks.
Yep, I don't see more questions. And has been 1 hour, so thank you, Tran. I appreciate your time for the seminar, and yeah, hopefully we can meet in person in the future.
Okay, well, thanks for inviting me.
Yep, thank you.
Bye.
See you. Bye bye.